The purpose of this video is to go over some total and net ionic equations and to give you a few more examples. Now, if you haven't watched the first video where I go through a deep dive of how to actually do this and why it's necessary, click on the card above. But for the rest of us, let's go ahead and go into some of these examples again. So what we need to do is we have a solution here where we've got silver nitrate reacting with potassium chloride to give silver chloride and potassium nitrate. Now, the first step in this, balancing the equation, which is actually already done, and then the next step is to identify each of these. And so, again, the whole purpose here is we should be able to categorize it as acid, base, or salt just by looking at its formula. If it starts with hydrogen, it's an acid. If it ends with hydroxide, it's a base. If it's neither, then it's a salt. And from that standpoint, I can see that none of these are acids. None of them have hydrogen as the cation. None of these are base. None of them have hydroxide as the anion. So all of these are salts. Now we have to use our solubility rules to figure out what kinds of salts they are. And so recognizing that I've got nitrate here, nitrate is always soluble. That means that this is going to be a soluble salt. And recognizing that potassium salts are always soluble, this is going to be a soluble salt as well. And so when I have potassium and nitrate together in the same product over here, obviously that will be soluble as well. So the question really falls into, what do we do with the silver chloride? Well, there's no rules governing silver. There is a rule governing chloride, and it says that chlorides are usually soluble. However, when mixed with silver, lead, mercury 1, chlorides are insoluble, and silver is one of those exceptions. So this is an insoluble salt. So now that I've identified everything, I go into writing my ionic equation. And my ionic equation is going to have silver ion, Ag+, reacting with nitrate ion, NO3-, and potassium ion, K+, and chloride ion, Cl-. Now, why did I do that? Why did I split all of those up? Well, again, remember our rules. If we have something that is a strong electrolyte, that would be a soluble salt, a strong acid, or a strong base. Whatever we have written as the molecular formula here is going to split into ions in our ionic equation. And so this is our ionic equation. Now on the other side here, we have silver chloride. Silver chloride is insoluble, so it's not going to split into ions. It's going to stay as a molecule, AgCl. And the potassium nitrate, since it is soluble, is going to split also. K+ and NO3-. So this is my ionic equation. All of the soluble, strong electrolytes have split. Those that aren't do not split. And here's what I have. Now, what I should recognize out of this is that there are some components here, the nitrate and the potassium in particular, that are common on both sides. Remember, we call those spectator ions. And those spectator ions disappear as we go from total ionic equation to net ionic equation. So in the net ionic equation, those spectators go away. I have silver ion, Ag+, reacting with chloride ion, Cl-, to make silver chloride, AgCl. Okay, So that's this one. Let's take a look at another example. And in this example, I want us to take special care and attention to a couple of details. First of all, we need to balance this thing. So for balancing, I'm gonna grab, let's see, I have 2 chlorides over here and only 1 here, so I need 2 chlorides. And now I have 2 sodiums and 2 hydroxides, so I need 2 sodium hydroxides. That looks like it's balanced now. Next thing I need to do is to identify the substances. So sodium chloride, I've got a sodium salt, that's a soluble salt always. In barium hydroxide, I have a hydroxide. Hydroxides are bases. I need to categorize this base. This base happens to be a strong base. Remember, all of your strong bases are your alkali hydroxides and your heavy, starting with calcium and going down the group. So calcium, strontium, barium, those hydroxides are strong bases. So this qualifies as a strong base. Here I've got sodium hydroxide. Sodium hydroxide, sodium is in group 1, so it's a strong base as well. And I've got barium chloride. Chlorides are usually soluble. The exceptions are lead, mercury 1, and silver. Barium is none of those. This is a soluble salt also. So for my ionic equation, I'm going to have, and keep in mind, coefficients carry over both ions. Subscripts carry over only the ions in the parentheses, or the ions to the element that it's attached to. So my ionic equation, I've got 2 sodium ions. I've got 2 chloride ions. I've got barium ion, Ba plus 2. I've got 2 hydroxide ions. On the product side, I've got 2 sodiums. I've got 2 hydroxides. I've got barium ion. And I've got 2 chloride ions. So if I look at this example, everything was a strong electrolyte. I had a soluble salt, strong base, soluble salt. Everything was soluble, everything was a strong electrolyte. So all of my substances were ionic. Now if I look closely, I've got 2 sodiums on this side and 2 on this side. I've got 2 chlorides on this side and 2 on this side. I've got a barium on this side and a barium on this side. I've got 2 hydroxides on this side and 2 hydroxides on this side. This is a rare circumstances where all the species are spectator ions. And so my net ionic equation is really simple. There is no reaction. How do I know that there's no reaction? Well, my products are exactly the same as my reactants. Nothing has changed. Nothing has worked its way through. There's nothing different on either side. If I take these 2 solutions and combine them, all I get is a more diverse solution that has more ions in it now than it did before. And so this is one of the reasons why we do net ionic equations, to tell us things like this. So let's go to one last example. I've got ammonium sulfate reacting with barium chloride to make barium sulfate and ammonium chloride. Now this equation's already balanced. What I want you to do, pause the video right now and try to work this equation out on your own. So categorize everything, make your ionic equation, turn it into a net ionic equation. So go ahead and pause right now. Okay, so here's how to solve this problem. And it's the same way that we've done all the rest. We already know it's balanced, so we need to categorize. Ammonium sulfate, that is a soluble salt because of the ammonium ion being always soluble. Barium chloride, we saw in the previous example, is a soluble salt. The chloride is usually soluble. Barium's not one of the exceptions. Barium sulfate is actually an insoluble salt. Sulfates are usually soluble as well, but barium is one of the exceptions to that rule. And the ammonium chloride is a soluble salt. So our ionic equation looks like this. We've got, so here is our total ionic equation. We can see that we have 2 ammonium ions plus a sulfate ion plus a barium ion plus 2 chloride ions. On the product side, we have barium sulfate insoluble, so it stays molecular. We have 2 ammonium ions and we have 2 chloride ions. To turn this into a net ionic equation, we have to identify our spectators. Our ammonium is common on both sides. Our chlorides are common on both sides. So those are going to cancel out. And so our net ionic equation is just what is left behind. Barium ion and sulfate ion react to make barium sulfate. And so total and net ionic equations are really just as simple as that. So just in summary, you always start with a balanced molecular equation. If you think back to that middle example that we did, if the equation was not balanced, if we did not treat it correctly, the spectator ions would not have canceled out and we would have ended up being confused. So a balanced molecular equation ensures that we always will be able to cancel out all the spectator ions and make sure that we're getting a complete picture. Once we've done that, we identify all the substances based upon their category, and we dissociate, we split apart all of the electrolytes that are strong electrolytes. And that gives us our ionic equation. To turn it into a net ionic equation, I need to cross out all of the spectator ions and write the net ionic equation with just the things that remain. So if you want some more practice, I strongly recommend going to these videos. I'll post links to them in the description. I'll also put little cards here on the display here for your benefit. You can just click through them and find the next resources. The next video will be an overview of how to assign oxidation numbers, which is a really important skill for general use into our next topic, which is oxidation and reduction reactions. Have a good day.